One thing I'm interested in, because this has certainly applied to designs that I've worked on, is how to deal with enclosures, right? And not necessarily when you have like a fan, but just how to deal with an enclosure in any kind of thermal analysis. And the reason I bring this up is because I've worked on some boards, they're power boards, and they get hot, but they're at least within spec when you just have them on the bench in the lab, right? So that's, closer to the situation that you're talking about. But once you put them in the enclosure basically turns into an oven because the enclosure is not a very good conductor of heat. And even if it was, it still has to heat up very hot before all of the heat starts to dissipate in the enclosure. So what's your advice for dealing with that kind of situation, and can your software actually help deal with that situation?
It can help, but of course it's not as precise as without enclosure. So I've got empirical experience from the past to companies I worked before. There we had also thermal simulation using airflow and the complete 3D geometry. And the experience from that period, of course, is somehow incorporated in my software. Typically, if you add a completely closed enclosure, the heat increase or the temperature increases by a factor of 2.
Today we're talking with Johannes Adam, CEO of Adam Research. We are very happy to have Johannes here today because he produces a piece of thermal simulation software, and I've been getting into thermal discussions much more recently, so I'm very happy to have Johannes on today. Johannes, thank you so much for joining us.
Thanks for having me.
Yes, absolutely. So as I mentioned, you do produce a piece of thermal software, and I think you are well known in some corners of the industry. You were recommended to come talk to me by someone else I know on LinkedIn. So before we start talking about all things thermal analysis, if you could just briefly introduce yourself for our audience.
Hello, everybody. Welcome to a thermal session on printed circuit boards. It's not a very widespread topic in electronics design, but it's of course necessary to know about it. How hot will my components get? What about our traces? What about the influence of temperature on voltage drop, for example? And that's what I'm doing. So my software is focusing on calculating the temperature created from heat, and the heat is created by the current in the traces, or the heat created in the components, or all together, and so on.
Okay. I would agree to some extent that thermal is often, I guess, an afterthought. It's not something that is always taken into account early in the design process. And um, I think that there are some challenges with that. Part of it is the access to thermal simulation methods and software packages. Um, some teams rely on something like ANSYS, and it's a complex CFD simulation, and you have to have a lot of expertise to be able to do that. Um, what do you see as one of the challenges with getting access to the thermal simulation tools that's needed to do any kind of thermal management earlier in the design process?
That's correct, you said. It must be as easy as possible. And that's what I'm trying to offer to the community. Forget about meshing also, complex finite element meshing. Meshing is one number. That's the so-called resolution. The other part is standard design or fabrication data like Gerber files or drill files. So everybody in the community could use my software independently of the provider of the CAD system. And then the other point is, what about the amount of data you have to give? I'm reducing this also to a minimum, not to what is needed. For example, just enter the watts for a component or set the amps for a net for a signal and press the run button. This is the simplest approach if we want to have an accuracy of plus minus 10%. Yeah. If you want to be more precise, then you have to think about temperature dependence of materials, temperature dependence of the external air cooling, and so on. But if the power of the components and the currents or the RMS current is correct, then the result is plus minus 5%.
So, it sounds like you are actually doing a kind of thermal simulation which aligns with really a lot of electronics designs. Most of the designs that I've worked with or that I've seen from folks who watch the channel, or from people who send in their designs for reviews, they don't use a fan, right? So they basically have stagnant air around the design. Maybe there's an enclosure, but typically they're just looking at the board in isolation and everything is static. So that sounds like the situation that you're actually simulating, and it's pretty broadly applicable.
That's correct. It's the laboratory situation where you know the ambient temperature precisely, you know it's still air, in quotes. And experience shows that if you compare with the infrared camera, the calculation is precisely matching the infrared, plus minus 5%. Any infrared camera has some error margin or so, plus minus 2 degrees Celsius or 2K, and that's pretty fine.
So at that level of error, it sounds like just a simple static model is good enough. So I'm always kind of curious as to why people haven't gone out searching for these kind of much simpler simulation packages, and instead they'll go for something like an ANSYS or a CST. I mean, like, ANSYS has great capabilities and everything, but it sounds like you're trying to use a nuclear weapon to kill a fly, if you will, right? Just to get a temperature distribution.
Yeah.
So is there like a distrust of these, I guess, simpler thermal simulation packages?
Maybe it's a problem of market penetration. ANSYS is on the market since 30 years, 40 years, don't know. And that's, they also, so if you address ANSYS, we talk about mechanical engineers typically. Yeah, because ANSYS is coming from the mechanical simulation, and this heat stuff in electronics is an add-on, so to say. And any mechanical engineer learns about ANSYS in school or in university, so they know it and they stay with it. That's why I'm happy to have this session to make my software a little bit more popular or known to the other outside of the world.
Yeah. So about your software, right? First, there's a couple of things that I think are unique or very helpful. One is that there's some automation, which you alluded to. And then the other is that there is a plugin to Altium Designer. So if you could just tell us a bit more about your simulation software.
Yes, that's what I want to add after the, sorry, stop. That's correct. We have a button called Altium to TRM. You press the button and it's automatically creating the data we need. But even more, if you have parameters in Altium, or our parameters like watts for a component or current for a trace, those data are also exported and then almost automatically imported with another button. So that's quite a straightforward process. It works for multi-layers, of course, buried through-hole drills, buried, blind, back drills. So the typical technologies. There's no limitation on that. Yeah, and when you after the import into TRM, you will see it in the demo. Then you can add or modify everything you want. Yeah, for example, the thickness of layers or the watts, of course, the currents. You can move components, which is not, of course, doesn't make sense in a design. Exchange the layer files, whatever you want. And of course, you can add transient features, which we haven't talked about, or a heating curve with steady state temperature, steady state power or current. And you want to know how long does it take until 150 degree, for example. Or will we have a thermal runaway, which is also possible if you enter ridiculously high currents, or non-ridiculously if you have a surge, so a pulse of voltage, for example, for 100 milliseconds, and you want to know what is the effect on temperature in that layer or net or signal. At the end, of course, after the calculation is more or less fast, typically a minute plus minus, minute, half a minute, 2 minutes. And then you get a series of images or pictures or diagrams with calculated temperature, calculated current density, and calculated voltage. And of course, there's an interactive mode where you select what you want and zoom and change the color bar and so on.
So you incorporate component packaging information into the simulation, like for example, the thermal conductivity of packages.
Yeah, there's a default that's a black box with a predefined conductivity. If you have the junction case or junction top or junction board thermal resistances, then of course you can add them and also have an underfill if you want between board and component. Or you can add a heatsink on top of the component just by searching in the vendor catalog and look for the thermal resistance of this heatsink.
And then you had mentioned transient heating, which I think if you're looking at a simpler simulator that's just going for the steady state temperature, that's not something that's often addressed. So you mentioned things like voltage or current surges. I could also imagine external temperature surges, so you very quickly go into a hot environment. It sounds like it
Correct.
doesn't really matter. You can just change one of the parameters and then look at the steady state, the transition between two different steady state levels.
That's correct, yes. Yeah, that's correct. A typical experience. Some aerospace guy asked, "What happens if lightning is hitting my plane and creating a 1,000-volt surge in 100 milliseconds?" And I got the design, and the event took place in some inner layer, yeah, for some reason. And then after the first calculations, I looked at the result and said, "Oh, the board is cold. What's the problem?" But it's cold on the surface and not inside in layer 4 or 5, because in 100 milliseconds, heat doesn't have enough time to escape from the spot of lighting of ignition and to reach the surface. So no infrared camera would be able to detect the problem other than the simulation.
I see. I see. And then there was one more question that I had about the capability. You had mentioned modifying certain things in the design in the simulation. So, for example, you could take like an iterative approach. You could, let's say, cycle through different layer thicknesses, things like this,
Yeah.
in order to then figure out for example, what is the most optimal transient type of response? What's the optimal temperature distribution in the steady states? Things like this.
Yeah, not only the layer thickness, also prepreg thickness and prepreg materials. Prepreg material, that's thermal conductivity, yeah, and in the transient case, density and specific heat capacity. It's always difficult to get those numbers. Not the thermal conductivity, you find that in the data sheet, if you believe it, but specific heat is quite difficult.
Well,
But
you said
it's not impossible to get reasonable results.
well, you said if you believe it with the data sheet. Tell me more about that.
I'm not an expert on data sheet cheating, but of course every vendor wants to have wants to show his best and so on. So typically, typically the thermal conductivity of a prepreg or FR4 is 0.3 watts per meter Kelvin. That's the unit, and yeah, the better ones go up to 1 watt per meter Kelvin, so 3 times more. But you cannot expect a temperature reduction by a factor of 3 if you increase the thermal conductivity by a factor of 3. That's not possible. It's not proportional, because
It's asymptotic, right? It's in the heat equation, right?
yeah, but it's not yeah, it's some root of something of the thermal conductivity. So typically, if you increase conductivity by a factor of 2, you get a temperature reduction maybe of square root of 2 or 1 over square root of 2 or even less. That depends on the distribution, of course, of the copper in the layers and the distribution of the heating components. Yeah? If the components are all concentrated in one spot, yeah, what should be the heat spread? What is the heat spreading able to do if it's not spread, or if the components are almost equidistantly distributed on the board, then the components itself produce the heat spreading, and there is no way for extra copper or extra special FR4 to add more heat spreading. That's
Sure.
the typical experience a beginner has to learn, and he will learn with the software.
Well, I think now is probably a good time to jump into your demo. So let's go ahead and cue that up, and we'll see some of the cool capabilities of your software.
This is the 2D view seen from top layer. Our intention is to bring current from this point somewhere here using the 5-volt net. And there are several methods to assign amps to pins and pads. Option 1 is to use the schematics. Let's have a look at the power schematics. And we see here some parameter name TRM, a label 2, and a value minus or negative 2 amps. This means that we are receiving 2 amps in pin number 2, starting anywhere in net 5 volt. I'm opening the LCD panel, and we see 5 volt nets arriving at pin number 2 and pin number 15. We assign another parameter called TRM. Pin number 2 delivers 1 amp, and pin number 15 the other one. How to assign the parameters? Go to property table. You create a parameter name called TRM and a value like a string. Pin number 2 1 amp, semicolon, pin number 15 the other amp. That's one way to assign the values. The other route is using the parameter manager. The parameter manager is a table containing pins and nets and parts. Here you see what we assigned. We also see another physics variable called the power, 0.5 watts to U6. Now we want to export the data. For the simulator, press a button, the rest is done automatically. I will now import what we exported in Altium. This is quite easy. Just open the wizard, the Altium wizard, and say forward, start import. Data are available. Let us inspect. This is a three-dimensional model of the board, starting with the top layer and dielectric and bottom layer. Drilled files, red ones, plated through holes, black ones, not plated through holes, and the components. Intentionally, the z-axis is stretched by a factor of 5 so that we are able to see what happens in between the layers. What else do we have? We imported the layer stack with the thickness of the layers as given in the Altium layer table. We have a bunch of drill files, individual drills, in that case 332 plated and 9 non-plated through holes. All the parameters, the plating, the drill depth, etc. can be modified. There's also actions here in the drop-down menu. Create a pattern out of a parent drilled hole. At the end, the final and most important table is what we call the loads table. This is a list of objects, like the components, and physical definitions like the watts and the amps. This list is starting with the components. Then we have a bunch of so-called pins. Those are the wires. Then we have a colorful table with representatives for the netlist. This object is number 39 of U1, and this pad is member of the ground net. Here we see what we defined in the parameter list in Altium, twice plus 1 amp at LCD1 and negative 2 amp at a connector pad. Data are available in the component list, in the watt column, 1 watt, 0.5 watt. There's a filter where we can rapidly search for the definitions, say amp not equal 0 or watt greater than 0. And all of a sudden we have an overview of the values we defined in Altium. Of course, it's possible to define the values here as well. Let us search for the use. We want to define another watts for U4 and U5. Let's assume 0.2 watts, and that's it. There are more actions available in this list. Activated by a drop-down list, we can change a bunch of values with just numbers, or copy, duplicate, export, import, and much more. The next step, of course, is to define the environmental conditions. Let's assume a lab temperature of 30 degrees. Calculate. That's it. Start calculation. It will start calculating the electric potential in our 5-volt net, given by the plus and negative amps. The current density is derived, defining the local power in a net. The power of the nets is combined with the power in the components. Finally, we'll come to a temperature. Now let's watch the results. Those plots come for free. It's not necessary to do extensive post-processing. Top layer, dielectric, bottom layer. This is interesting, looks like a trace. It is a trace, visualized by voltage. We start here with negative 2 amps in blue, then changes layer, current density is like this. There's also some 3D visualization available. And of course the voltage. And the drilled holes to visualize the up and down of the current in the three-dimensional model. The report file has all results in a table. This file is also available on hard disk. There are much more options than can be shown in this video. For example, transient modes, temperature dependent mode, and a lot of extra stuff.
Okay, so I think very interesting. I like the plugin directly to Altium Designer. One thing that I'm always interested in when I see these kinds of tools that integrate with Altium Designer is what's the user response? How have users that you've talked to responded to having that kind of plugin? Do they see it as, a good way for them to get some insurance that a design will work somewhat to spec earlier in the process rather than, going through a prototype and then finding out that their board is too hot?
Yeah, also first of all, every user who worked 2 weeks or so is fascinated about how easy it is to get results. The learning curve at the beginning is quite steep, but you learn after years some subtle effects or the demands coming from the product you are designing. Yeah, it depends. There are I have users who are really using the software in the beginning of the design phase, even starting without Altium designs or very coarse designs without netlist and so on. They place some components, have some ground and power planes, and want to see what is the best position for the components, or they have a draft of the net list of the nets and signals and want to know what is the current or density or heat we can expect from the traces. You have to keep in mind that thermal is one part in the design process. Yeah, we have EMC, signal integrity, cost, manufacturability, marketing, design, the design, the real design, and so on, the shape of the board and the size of the board. And that's why a thermal engineer should be included in the design process as early as possible, if possible, and not in the end as a firefighter when the PCB gets too hot.
Sure, yeah. I think you brought up something important here, right? Because you don't necessarily have to wait until the layout is fully complete, right?
Correct.
You brought up a situation where you have a proposed placement, and then you at least have the planes identified, right? And the planes are easy to switch around in the layer stack. It doesn't really affect anything. So I think that's a really good time to start analyzing what could the potential not power distribution, but the temperature distribution be in this design once it's actually running.
And that's very easy and can be done in the second day of use of the software. In principle,
In principle, yeah. So where can users go to get some resources to learn more about your software and get access?
Yeah, best is to go to my website. It's www.adam-research.com. There I have a lot of examples and material, academic material, practical material, and a contact page where a demo license or a demo or a live demo can be ordered or requested.
Now, one thing I'm interested in, because this has certainly applied to designs that I've worked on, is how to deal with enclosures, right? And not necessarily when you have like a fan, but just how to deal with an enclosure in any kind of thermal analysis. And the reason I bring this up is because I've worked on some boards, they're power boards, and they get hot, but they're at least within spec when you just have them on the bench in the lab, right? So that's, closer to the situation that you're talking about. But once you put them in the enclosure basically turns into an oven, because the enclosure is not a very good conductor of heat. And even if it was, it still has to heat up very hot before all of the heat starts to dissipate in the enclosure. So what's your advice for dealing with that kind of situation? And can your software actually help deal with that situation?
It can help, but of course it's not as precise as without enclosure. So I've got empirical experience from the past two companies I worked before. There we had also thermal simulation using airflow and the complete 3D geometry. And the experience from that period, of course, is somehow incorporated in my software. Typically, if you add a completely closed enclosure, the heat increase or the temperature increases by a factor of 2 or a factor of 3. That's typically. Another point which can be done with the software is consider you have a space application without any airflow and so on, and you rely on bolts or screws or some other metallic connections from the board surface to the imaginary cooling item. It's of course possible to add this screws and bolts and fixations manually in my software and say, okay, you are permanently 200 kelvins and now let us investigate how the heat, or whether the heat at all comes from, whether the design is so that the heat can have a path from the component to this fixed point of temperature. So,
Oh, I see. I see what you mean. Yeah. So what's the heat transfer path from the source to, say, the mechanical element that you're using as a heat sink?
yeah, and typically that's a very hard. It's typically it's very difficult to get the heat from here to here. Yeah. So let us assume here's some frame at known temperature, metallic frame, and of course all these traces and non-traces in between are impeding the heat to be transported from the source to the heatsink in the frame.
I see. I see. Okay. Yeah. So what can be done about that in those situations? I mean, is it just, more copper? I mean, do you have to like put notches in the copper that's being used to transport heat?
Yeah.
Because that kind of goes against what you might do electrically. Let's say that the main heat transport element in the board is a plane, right? But you
Yeah.
want the heat to go to this screw,
Yeah.
and how do you get the heat to go that way? Do you like cut notches in the plane? Do you use dedicated connections between those regions?
Yeah, there should be a continuous plane between source and sink, of course,
Right.
without any interruption, and of course as close as possible to this sink. It's a very
Yeah.
difficult task. In in the civil airplanes, this technique is called wedge lock cooling.
I see.
Yeah.
Yeah.
And that's my experience from a couple of consulting projects, that it's almost impossible to bring heat from the center to the periphery. But in an airplane, we always have ventilated cabinets where the heat is then taken by the airflow.
Yeah. This is, I think, a good reminder for folks who want to get into aerospace that the thermal issues can be greatly compounded by the fact that you don't have the airflow, and you do have to rely on things like the enclosure, especially when you're working in vacuum.
Yeah, and if the air conditioning breaks down, what then?
Yeah, exactly.
For some reason,
yeah. Well, this has been extremely informative, as always. I love getting to take a look at some of the software that folks create that integrates with Altium products. So I'm very happy that you came on today. One more time, tell everyone where they need to go to get access to your software.
Yeah, go to my website, www.adam-research.com, and the contact page, and enter your name and your email, and you will get a download link. And of course, you need a license file, which is also can be applied there.
Excellent. Well, I hope everyone that's listening will go out and go to adam-research.com and take a look at this very cool simulation package. Johannes, thank you so much for being with us today.
Thank you for the invitation.
Absolutely.
Bye.
Absolutely.
Bye.